Okay, so mode 1, excessive descent rate. And let's just watch the video again.
Mode 1 alerts flight crews to excessive...
Now, are you guys getting the audio?
Yep, it's coming through.
Okay, that's good.
...rates of descent when the aircraft is near terrain. Using radar altitude and rate of descent information, the ground proximity warning computer monitors the flight profile when an aircraft is within 2,500 feet of terrain. Should an excessive rate of descent develop for the aircraft's current altitude above ground level, the red GPWS warning lamp will illuminate and the voice alert sink rate will be heard.
Sink rate. Sink rate.
If the rate of continues or worsens, a continuous pull-up voice warning will be heard.
Pull up. Pull up. Pull up.
As the aircraft recovers from the excessive rate of descent, the red GPWS warning lamp will extinguish and the voice warning will cease.
Okay, that's mode 1. Go to mode 2, excessive terrain closure rate. And
Mode 2 warns flight crews of excessive closure rates with rapidly rising terrain. Using airspeed, rate of descent, and radar altitude, GPWS compares terrain below the aircraft to the flight path. If terrain rises significantly within 2,000 feet of the aircraft, a closure rate is measured. When the closure rate shows danger to the aircraft, the red GPWS warning lamp will illuminate, and the voice alert terrain will be heard. If the closure rate continues or worsens, the voice call-out will change to a continuous pull-up warning until terrain is no longer a threat.
Terrain, 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 terrain. Pull up.
To help ensure sufficient recovery, the red GPWS warning lamp will remain illuminated until the aircraft climbs 300 feet above the altitude where the last pull-up voice warning was heard.
so mode 3, altitude loss after takeoff or go around.
Mode 3 warns flight crews of inadvertent descents and loss of altitude after takeoff or during a missed approach. GPWS recognizes a takeoff or missed approach using aircraft speed, radar altitude, barometric altitude, and aircraft configuration changes. GPWS then monitors radar altitude and barometric altitude during the initial climb-out. Should the aircraft descend, GPWS compares any loss of baro altitude to peak altitude gained. When this difference is roughly 10%, the red GPWS warning lamp will illuminate and the voice alert "Don't sink" will be heard.
Don't sink. Don't sink. Don't sink.
When a positive rate of climb is re-established, the red GPWS warning lamp will extinguish and the voice alert will cease. Once the aircraft has gained 1,000 feet above ground, Mode 3 is disabled. When GPWS again detects a takeoff or missed approach situation, Mode 3 protection is automatically re-enabled.
So mode 4 subdivides into mode 4A, landing gear, and mode 4B flaps. So let's look at both of those.
Mode 4 provides minimum terrain clearance protection in all phases of flight. GPWS will alert the flight crew to insufficient terrain clearance based on airspeed, altitude, rate of descent, and aircraft configuration. Mode 4 protection is especially valuable when the aircraft is on a normal flight path, where excessive descents or closure with terrain are not a factor. To understand the scope of Mode 4 alerts, let's follow a typical flight from takeoff to touchdown. As shown a few moments ago, Mode 3 protection is automatically enabled as the takeoff occurs. At the same time, Mode 4 begins to build a floor below the aircraft during climb out. This floor will continue to build under the aircraft until reaching roughly 800 feet above ground, where it will remain throughout the flight until the aircraft begins initial approach at the destination. If the aircraft penetrates this floor during the flight, the red GPWS warning lamp will illuminate and the voice alert "Too low terrain" will be heard.
Too low terrain. Too low terrain.
Once the aircraft is safely back above the protective floor, the red warning lamp will extinguish and the voice alert will cease. During the approach and landing, GPWS monitors airspeed and aircraft configuration. The minimum terrain clearance floor is automatically adjusted as airspeed is decreased. If landing gear is not down and locked at 500 feet above ground, the red GPWS warning lamp will illuminate and the voice alert "Too low gear" will be heard.
Too low gear. Too low gear.
If flaps are not set to landing configuration by 170 to 250 feet, the red GPWS warning lamp will illuminate and the voice alert "Too low flaps" will be heard.
Too low flaps. Too low flaps.
Pilots may elect to disable the flap alerts by engaging the flap override function either prior to or during a flap alert enunciation. This allows landings in configurations other than normal landing flaps with no GPWS flap alert.
Okay. So Mode 5 is excessive deviation below the instrument landing system slope. Let's have a look at that one.
Mode 5 provides protection for inadvertent descent below a glide slope while on an ILS approach. GPWS monitors the flight path in relation to the glide slope centerline while on the ILS final approach course. Mode 5 glide slope alert is enabled when a nav receiver is tuned to an ILS frequency and receiving a glide slope signal, landing gear is down, and radar altitude is less than 1,000 feet. Should the aircraft descend below the glide slope to a 1.3 dot fly-up indication, the amber GPWS glide slope alert lamp will illuminate, and the voice message "Glide slope" will be heard.
Glide slope.
Glide slope voice messages are initially softer and less frequent than other GPWS alerts and warnings, but become louder and more frequent as the aircraft deviation below glide slope worsens.
Glide slope.
Once a correction is made by the pilot and the aircraft is returning to the glide slope centerline, the amber glide slope alert will extinguish and the glide slope voice alert will cease. To allow repositioning below glide slope when visual conditions are or on localizer-only approaches, pilots may elect to disable the Mode 5 glide slope alert function. This is done by depressing the amber glide slope alert lamp or switch either prior to or during a glide slope alert enunciation.
Okay. Mode 6 is altitude and bank angle protection.
Mode 6 contains altitude and bank angle call-out functions designed to increase situational awareness for the flight crew. These call-outs are selected by the customer when GPWS is initially installed in the aircraft. The decision height minimums call-out is a function of radar altitude. The pilot sets the radar altitude bug or DH manually, and GPWS provides the call-out minimums at the selected altitude on the approach to landing.
Minimums. Minimums.
Altitude callouts can be chosen from a large menu of possible combinations.
500.
These callouts are provided to pilots as a means to confirm aircraft position during approach.
100.
These callouts are just an example of one altitude callout menu. Bank angle callouts are designed to alert flight crews to the possibility of overbanking, which may lead to serious flight path deviation or loss of control. These callouts occur at preset maximum limits tailored to the aircraft type.
Bank angle. Bank angle.
Near the ground, radar altitude is used to advance the bank angle alert, so callouts are given sooner, providing additional time for pilot corrective action.
Bank angle.
Okay. And mode 7, which they're saying is one of the highest priorities, is wind shear.
The Mark 5 and Mark 7 GPWS offer detection and warning for encounters with wind shear up to 1,500 feet above ground. GPWS uses airspeed, radar altitude, barometric rate, angle of attack, air temperature, vertical and longitudinal acceleration, and aircraft-specific performance information to detect encounters with severe wind shear. When an aircraft first encounters the strong headwinds, decreasing tailwinds, and vertical updrafts associated with the outflow of microburst activity, the amber GPWS wind shear alert lamp will illuminate and remain on as long as the condition persists. Some installations will also enunciate the voice alert.
Caution. Wind shear.
If the aircraft enters the area of microburst activity where headwinds rapidly decrease, tailwinds increase, and vertical downdrafts become severe, the red GPWS wind shear warning lamp will illuminate. A short two-tone siren will be heard, followed by the voice warning.
Wind shear. Wind shear. Wind shear.
GPWS lamps and voice warnings will cease when the aircraft is no longer in the wind shear condition. Recovery should always continue to a safe altitude above terrain.
Okay. And then we went into enhanced ground proximity warning systems. Was here, where you have your own independent screen, or it can be superimposed onto your weather radar screen or an EFIS screen. And look at that.
Because the overwhelming majority of controlled flight into terrain, or CFIT accidents, occur near an airport, and the fact that aircraft operate in close proximity to terrain near an airport, the terrain database contains higher resolution grids for airport areas. Lower resolution grids are used outside airport areas, where aircraft en route altitude makes CFIT accidents less likely, and terrain feature detail is less important to the flight crew. With the use of accurate GPS or FMS information, the eGPWS is provided present position, track, and ground speed. With this information, the eGPWS is able to present a graphical plan view of the aircraft relative to the terrain and advise the flight crew of potential conflict with the terrain or obstacle. Conflicts are recognized and alerts provided when terrain violates specific computed envelope boundaries on the projected flight path of the aircraft. Alerts are provided in the form of visual light enunciation of a caution or warning, audio enunciation based on the type of conflict, and color-enhanced visual display of the terrain or obstacle relative to the forward look of the aircraft. The terrain display is provided on the weather radar indicator, EFIS display, or a dedicated eGPWS display, and may or may not be displayed automatically.
Okay. And this one as well.
Hi, welcome to the short video on WingX Pro 7's new passive radar altimeter. It's a great new feature if you're flying in mountainous terrain, over hills even, and on instrument approaches. You want to see what the terrain is doing directly below you. What I've done is set up a flight simulation from Lake Tahoe Airport down into San Jose International. We are track up, so even though we are flying a heading of 210, we're flying straight up the screen. Notice how the identifiers are rotated correctly so we can still read it, and we even forget that we're actually looking at a rotated sectional, so that's very nice. Top left-hand corner tells us how high the terrain is, 7,700. You'll notice that it just turned orange, which means that we're below 1,000 AGL. And when it turns red, that actually means that we are below 500 AGL. And you'll notice that that corresponds with what we're seeing on the moving map. If we tap on the passive radar altimeter and say show approximate AGL, instead of it saying terrain, it'll say approximate AGL, and that is telling you the distance between the aircraft and the terrain. One warning that needs to be mentioned is that this assumes that the GPS altitude that you're showing up in the top right, on top of the screen over there, is accurate. So the responsibility is yours to ensure that this altitude matches what you're seeing on your altimeter. But assuming that they are correct and they match up and everything's good there, this approximate AGL is actually very, very nice, very accurate, and highly recommended to use when you're flying over mountains. And like I said, instrument approaches are great too, just to ensure you're not getting too close to the terrain, or when you're getting vectored around on an instrument approach. How do you know that ATC is not vectoring you into a hill or a mountain? That it has happened. Fortunately, it doesn't happen very often, but just for peace of mind, we strongly recommend using the passive radar altimeter and continually looking at it while you're on the approach. You'll notice that we put all the important information up at the top. We don't spread it around the screen. You have, just like you'd be looking at it in an aircraft, you have your heading in the middle, your airspeed on the left, your altimeter on the right, and all your numbers there. You'll notice that your heading and your desired track to San Jose are directly below one another. So we make things very simple to read, and the passive radar altimeter is right there up in the top left-hand corner.
Great. So let's not forget all of our different sounds for this system, thanks to Boeing.
Glide slope. Pull up. Wind shear. Wind shear. Wind shear. Terrain. Terrain. Pull up. Sink rate. Pull up. Terrain. Pull up. Don't sink. Don't sink. Too low. Terrain. Too low. Gear. Too low. Flaps. Too low. Terrain. Glide slope. Bank angle. Bank angle. Minimums. 500. 100. 50. 40. 30. 20. 10. Wind shear. Wind shear. Wind shear. Too low. Terrain. Caution. Terrain. Caution. Terrain. 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 Pull up.
There you have it. So if while you're doing your 100-question final exam, okay, one question comes up with one of those sounds and I say select which mode it is, that'd be fun, wouldn't it? Unless, of course, it was something like glide slope. That'd be a giveaway. What mode is glide slope, though? Huh. And it all went silent. Say 5. escape from this. Second. So again, for those who, I see most of the folks are here now. For those of you just coming in, don't forget to do the attendance quiz. Let's get that out of the way. And that for a second. Okay. Lynn, you still out there?
Morning, Darren. How are you?
Good. Are you hearing everything okay?
Yeah, got it. 5 squares here.
Okay, that's great. Okay, so let's just have a look here at some antennas. That audio coming through okay for people?
I don't hear anything.
You don't hear anything. Okay, hang on. How about now? You hear that? You guys hearing that?
Nothing.
No.
Oh, hang on. Let me go back and see what's going on here. And try that again. Back to there. Okay, up now. Are you catching that audio now?
Yeah.
Yep.
Okay, that's good. Great.
Today's general aviation aircraft carry avionics often as sophisticated as the airlines. Consumer demand has spurred avionics manufacturers to use every available state-of-the-art device to bring performance to new heights. Your job as a systems installation designer is a key one in the optimum performance of the avionics system. But it
Are you guys now promoted to system installation designer? That's good news.
is often a job in which you may have to wear many hats. And one of the most important aspects is sometimes neglected: antenna location. The installation of a full complement of avionics often requires a series of compromises in the location of antennas. This program is intended to help you make those decisions easier by providing examples of antenna placement and some of the reasoning behind the particular location. Today's spectrum of radio frequency usage in general aviation covers the range from 10 kilohertz to above 9 gigahertz, as shown by this frequency chart. You should have one around your shop.
Yeah, ours is in Y149 at the back of the room. It's the Industry Canada chart. Nicely colored chart.
The broad scope of frequency usage and the limited installation areas available often challenge the ingenuity of the installer. Aircraft are made of metal, or in the case of fabric-covered aircraft, enough tubing to be considered metal enclosures. Radios installed within these enclosures can be considered to be trying to operate within extensive shielding, so antennas are necessary for signals to be transmitted and received. Antennas are required.
So is that a good idea? One comm on top, one comm on the bottom? What do you think?
Yeah, it looks pretty good.
Sure. What's the frequency range of our basic VHF AM comm transceiver? From where to where?
118 to 137.
Yep, 118 to 137. Sounds about right.
For virtually every system on board. In order to launch and capture radio signals, antennas are basically metal devices designed to operate in their respective frequency.
Why the transponder and DME so far away from each other, those two small antennas?
They're both pretty high power.
High powered, and they're in the close proximity to the frequency range, right? Transponder is operating 1030 for receive and 1090 to transmit, and DME is about, I don't know, 978 to about 1213 officially. So you want to keep those. You want to keep those two definitely more than 2 feet, 2 feet or more apart. Same with the COM and the VOR. Remember, COM is 118 to about 137, but below COM is nav, and that's from 108 to about 118. So we want to keep those two away from each other as well. So this seems to be decent placement here. Glide slope on the nose, so we don't have any scalloping. Marker beacon at the back, maybe center line. Yeah, that seems to be good.
Bands by being resonant. A given antenna may be able to capture signals, send them, or both.
One question, or one bit of information. If an antenna is not performing very well for transmitting, it won't perform well for receive. So if it's a dog when it transmits, it'll be a dog when it receives.
The antenna should correspond to the operating bandwidth of the radio. Many antennas are referred to as broadband, and this generally applies to comm systems that operate from 118 to 136 megahertz.
Now that's an old. This is an old video. That was when the comms used to end at 135.975. We know now they're up to 136.975. So there's an extra megahertz on the band there.
And can include 360 or 720 channel radios.
What's the number of channels now?
$760.
Yep, 760. Good.
Some older 90-channel transceivers are still in operation, and they use bare whips that are cut for 118 to 127 megahertz. We still find some aircraft with avionics updated to the 118 to 136 megahertz bandwidth, but still equipped with the old style antenna. You
notice the way they draw this here. Remember I told you when it comes to antennas, these broadband antennas, it's kind of performs like a skirt. It's the antenna performs reasonably well, sort of in the center frequencies, and then it tapers off at the low end of the spectrum and at the high end of the spectrum. So don't expect as good a performance, let's say at 118 and 137 nowadays, as you would in the middle. They seem to perform better in the middle. They're designed that way.
Owners are not getting the performance they paid for. These installations should be updated to a newer antenna compatible with the transceiver.
So what they're saying there is don't use an old antenna, let's say one broadband cut from 118 to 136 when you now have a radio that goes to 137. Okay, upgrade your antenna.
All antennas have gain, whether a plus or minus gain. Antenna value is measured in dB above or below a reference. Impedance is the ratio of voltage to current. Expressed in ohms, it is the opposition offered by an antenna to the flow of alternating current.
What's the impedance of pretty much most aircraft coaxial cable, and for that matter, the antennas? Well, I'll give you some choices. Aircraft coax, is it 75 ohms, 50 ohms, 73 ohms, 36 ohms? What's aircraft coax?
73.
No, that's the Hertz antenna. Remember, 50 ohms. And what kind would we use as far as the color? Are we using black or brown?
Brown.
Brown, because the black stuff is got polyvinyl chloride and it's toxic. So we go to the brown stuff. It's better anyways. So it doesn't matter whether it's the smaller brown stuff or the bigger brown stuff. 50 ohms is 50 ohms. And we all remember the formula. You remember the formula for unbalanced transmission line to get that 50 ohms? I believe it was a constant 138 over the square root of E times the log of, maybe D over D, whereby one of those D's is the diameter of the interconductor and the other D is the outside diameter of the shield. So that forms the basis for the impedance. Why is it so important that the coax maintains a constant impedance? Well, it's because the antenna is a 50 ohm antenna. In order for maximum transfer of power to happen from a 50 ohm transceiver, you need a 50 ohm cable, okay, for all the energy to transfer from the source, which is in this case is the transceiver, to the load, which is the antenna. If you don't have a perfect match, you have standing waves, and standing waves are bad, and it spawns, basically energy coming back towards the generating source, and in time destroying it. Okay, so we want all the energy to transfer from the source to the load, and none of it ever coming back in the form of standing waves. So that's why we have to match everything perfectly if we can. And we can live with some standing wave ratio of about, I know our notes say, 3 to 1 is that once you get into there, it's awful, but you should start to get concerned with the system if it's spawning anything over about 2.5. You're slowly killing that radio.
The impedance must be compatible between the equipment, cable, and antenna to provide the maximum transfer of energy out into space. Antennas may be polarized horizontally or vertically. For maximum performance, polarization must correspond to that of the ground station antenna. The systems are well defined as to their polarization. For example, comms and DME are vertically polarized, while VOR and glide slope are horizontally polarized. This illustration shows that losses due to cross-polarization can work to our advantage. Voltage standing...
What does that mean? How can losses due to cross-polarization work to our advantage? Well, the answer is, vertically polarized antennas don't necessarily talk well to horizontally polarized antennas. And that's what we want. We don't want our comm, from 118 to 136.975 to be able in any way, shape, or form interfere with our nav, which is 108 to 117.95. We don't want it to be able to interfere. That's why one of them is vertically polarized and one of them is horizontally polarized. But more so, the horizontally polarized antenna is a directional antenna, and when you navigate, that's a nav antenna. You want basically that's what directional means. It means to navigate.
Wave ratio is a measure of the quality of the impedance match of the antenna to the rest of the system. The lower the ratio, the better the match, providing maximum transfer of energy. A 1-to-1 VSWR would mean all power was being radiated by the antenna and none would be reflected. Some of the energy flowing through an antenna is dissipated as heat or power loss. Efficiency is the ratio of useful output to input energy.
Yeah, so everybody knows the efficiency formula. It's POUT over PIN, power out over power in.
We can never achieve 100% efficiency. However, values greater than 90% can be achieved. Impedance, VSWR, and bandwidth all affect efficiency. Connecting a through-line watt meter in series with the antenna.
Now, looking at that watt meter, is that measuring forward power or reflected power right now?
Reflected.
Power
Yeah, how'd you know?
pointing towards the radio.
Yeah, so we're seeing any energy coming back.
Feed line will provide a good measure of the quality of the antenna system. Low reflected power indicates good radiation. The optimum through-line indication would be full forward power with none reflected.
What's the closest thing you can do to get that? Is it with an actual antenna or is it with a dummy load?
It's a dummy load, isn't it?
Yeah, because a dummy load is basically a perfect resistance. It doesn't have any like an antenna doesn't have any inductance or capacitance. So it's a perfect match. Usually you get very little coming back if you use a dummy load. Unfortunately, a dummy load doesn't make a very good antenna. Makes a great heater though.
There are 4 general types of avionics systems that utilize antennas. Navigation systems usually receive only. These systems receive and process ground or satellite transmitted signals. Communications systems, of course, transmit as well as receive. Airborne comm systems include high frequency, or HF, VHF comm, VHF FM, used to communicate with other services, and UHF radio telephone, which ties into the ground common carrier landline telephone system. Pulse information systems include DME and transponder. DMEs transmit a signal demanding a response from the ground station. Transponders transmit only when a demand is received from a ground station.
In the game of DME versus the game of transponder, in the game of DME, who is the interrogator? The aircraft or the ground station?
The aircraft is, right?
Yeah, so in DME, the aircraft is the interrogator and the ground station is the responder or replier. However, in transponder, air traffic control system transponder, the ground station is the interrogator and the aircraft transponder unit is the replier. It's opposite. That's what the guy's trying to say there.
The 4th type system is the radar system. The radar system is the only...
What 2 systems are we looking at? What's the one going down? This one.
Radar altimeter.
Radar altimeter. So that only starts working really when you're about 2,000 feet, 2,500 feet above the ground and then towards the ground. What's this other one out the front here?
Color weather radar.
Yep, color weather radar. How many colors in a color weather radar? In a good one?
4, 5, including black.
Okay, yeah. So 4, which is what's the most devastating color in a 4-color color weather radar?
Magenta.
Magenta. What color is magenta?
Pink, purple-ish.
There you go.
Only one that is not dependent on ground-based electronics. Radar altimeters can be considered a single-target, multi-range radar. Weather radar is a multi-target, multi-range radar, transmitting a signal and receiving that signal back from cloud precipitation cells. Communications antennas come in many shapes and sizes.
Okay, which one do I hate the most?
Bent whip.
You got it, that one. Of these 2 here, the one on the left and the one on the right, which one is higher speed?
The high-speed blade.
Yeah, so this one,
The
the
one
one
right.
with the one with the tougher shank. See this one here? That tougher shank is a higher speed than this one with the sort of the wimpy shank. And the highest speed one is this broadband blade on the top center.
They are basically quarter-wave monopoles.
Who invented that again? The quarter wave. Is that Hertz or is that who's the other guy?
Marconi.
Marconi.
Their length is a fraction of a wavelength for the frequency band of the transceiver. Once you get above VLF, Omega, ADF, and Loran bands, the physical size of the antenna decreases as you go higher in frequency. Not that lower bands could not use larger antennas. Practicality limits their size. Communication systems include the familiar standard VHF AM comm transceiver. The principles that apply to VHF also apply to the other communications systems found in aircraft. Except for the physical size of the antenna, the theory of operation and performance in these different bands are basically the same.
Okay. Let's have a look at those. I'm looking at all of those. And at least one of them, maybe even 2 of them, are unique in that they use a different mode of propagation. There's 3 modes of propagation: ground, space, and sky. Let's look at the first one. VHF AM, 118 to 136 megahertz, mode of propagation.
Space.
That's space, so that's line of sight direct. And keep in mind the newer ones go to 137. VHF FM, high band, 150 to 174. That's really 138 to 174 nowadays. Mode of propagation.
Also space.
Also space. VHF FM low band, 30 to 50 megahertz. But it's still VHF. What is it? Yeah, still the same as the first two. So that's still space wave propagation, line of sight. So these first 3 are space wave. UHF. What mode of propagation is something that's in the UHF band? Okay, I'll just start asking people randomly. There we go. Section 4. Let's go with Bradley Rope.
Hey, Dan.
Hey, you're there. What took you so long? You're pretty slow on the. You're never going to be good in a gunfight.
I'm not the cowboy kind of type.
You are now. See that 4-1 down, UHF FM, 400 to 512 megahertz? Give me a mode of propagation. Tell me whether it's space wave, sky wave, or ground wave.
Sky wave?
What's the sky? What's in the sky that you want to hit? So you want this to be hitting the ionosphere and bouncing back, this one here?
Yeah.
You do?
No,
oh, you
no.
You want another one on that page to be hitting the sky and eh?
Yeah.
Which one do you want? Yeah, I think you're mistaken that one for the very last one, HF. And for that matter, Citizens Band, 27 megahertz Citizens Band and 2 to 30 megahertz single sideband HF. These are the 2 weirdos in my view. These 2 here, they're the ones that are skywave propagation. You bounce off the ionosphere. And the other 4, the ones above that, are all line of sight systems, so they're space wave propagation. Good.
There is just so much real estate on aircraft. The space available to do a proper antenna installation is limited. Also, customers are conscious of their aircraft aesthetics, and you should pay nearly as much attention to providing an installation that fits the lines of the aircraft as you pay to performance.
What's this one on the right? Top right. Is that 1 antenna or 2 antennas?
Isn't that really horrible combination antenna that you hate, Darren?
I hate that one. That's the COM, which is probably in this older one. That's probably 118 to 136. And then the boomer is 108 to, well, 117.95. So that's the nav. Yeah, I don't necessarily like it. At least they mounted it center line. Now, what type of antenna is it? Is it a balanced loop style antenna, or is it a V style antenna, this one? Hitch, are you there? Where's Hitch?
I'm here.
Yeah, what is that? That top right?
Not quite sure.
I don't have a side view of that. But it has an apex, it has a point on the front, and it's center line. Your choices are, is that a balanced loop style or is that a V style?
Let's go with V style.
You got it, Pontiac. That's a V style antenna. So they don't perform as well anyways as a balanced loop style. You're saying, hey, what's a balanced loop style, sir? I don't know, that looks like a balanced loop down here. That's a towel bar on the other one. Cool.
Customers do not want flying porcupines or antenna farms. However,
So that's our problem. There's a lot of antennas that got to go on an aircraft, and you end up with an antenna farm. A lot of antennas in close proximity to each other.
this can be overcome by some planning and proper selection with both system requirements and customer in mind before you cut metal. Most antennas are speed rated. They are only designed for safe installation and durability up to a certain airspeed. A higher performance aircraft requires a higher mechanical strength antenna. Some precautions are required when placing antennas in close proximity to each other. VHF comm antennas in the same band should not be placed within 5 feet of each other.
So those two there.
As you go up in frequency, this distance can decrease. It is not possible in all cases to maintain these distances. However, it must be understood that performance can be degraded when antennas are too close. Many smaller aircraft nowadays are following the example of the larger aircraft, with one comm antenna on top and one comm antenna on the bottom of the aircraft. The customer should be told which system is which. He may not be heard because of blocking when he's on the ground using the belly antenna. While care should be taken in placement of antennas in the same frequency band, this is not too much of a problem with antennas placed in close proximity to other frequency bands. However, certain precautions should be followed. Spacing is important when placing comm antennas close to VOR antennas. Ideally, separations greater than 5 feet should be maintained. By placing comm antennas too close, or what is considered the near field, the other antenna, in this case the VOR antenna, will receive this energy and cause crosstalk, resulting in needle jumping or excessive scalloping. Bent-back whips have a high content of horizontally polarized signals and aggravate the VOR interference potential. There are also antennas that may serve another function, and this is the case of being used to attach ADF sense wires. Before attempting this type of installation, check with the manufacturer to assure that the antenna is designed properly.
Let's hope you don't have an ADF anymore, and let's hope that it's really not that old that it has a sense antenna. So this is the sense long wire antenna for the ADF system. There's actually a hole in this type of comm antenna to allow for the sense antenna to hook onto it. But let's hope you don't ever see that again.
Do not arbitrarily attach wires to other antennas. Present-day ADF antenna design virtually eliminates the need for this procedure.
And why is that again? Oh, because they're combo antennas. They're in that flat teardrop-shaped antenna now.
Close proximity of antennas to vertical stabilizers can have a negative effect on the radiation pattern. An antenna too far aft gives a pattern with a deep null aft, limiting reception from behind the aircraft. In the proper position, the effect of the stabilizer on the radiation pattern is minimized, virtually eliminating the null. The result is more omnidirectional reception and transmitting coverage. We recommend one VHF comm antenna on top and the other on the bottom. Better coverage can be achieved with the top and bottom mount rather than just duplicate radiation patterns from two top antennas.
Okay, so it's about 25 after on my computer clock. Let's go for our